of so-called breaking the ideal gas law, and have enough information now, we can start to understand the consequences of the fact that the ideal gas law, in some sense, is only ideal in one very small limit, right? Which is where, and we'll just, I've already closed out of my data, right? But we saw that ideal gases are ideal at two different limits. One is where the pressure is very low, meaning the average distance between everything is very large in your box, or the temperature is very high. And when the temperature is so high, you effectively have heat soak of your interactions. Things are moving so rapidly, there's so much kinetic energy that any perturbations due to the attractive or repulsive potentials in between molecules are just negated. You soak everything out. And so when you just have heat energy, then Pivnert applies again, and the ideal gases occur as well. So ideals are hot or very low pressure. And of course, most chemistry is cold in a relative sense and at high pressure. And by high pressure, I mean a bar, an atmosphere. That's high pressure. What I mean by low pressures, I mean microbar, nanobar. That's what we mean by low pressure. It's vacuum, not condensed. So in the world of 1%, the 1 bar, 298 Kelvin world, ideal gas law at best works maybe a couple % error. If you have helium or nitrogen, gases that have a lot of interactions, we get agreement to within a few %, but anything else, it fails miserably. And there's a particular feature about gases that the ideal gas law does not predict at all. And I want to talk about that today. That one crucial feature of any material that is at some point a gas can also be at some point not a gas. Be a liquid, be a solid, right? There's phase transitions. But as we'll see, the ideal gas law has no phase transitions. The ideal gas is always gas. So let's look at that today. So what I want to introduce today, we're going to look at it from a couple different perspectives. But let's just tackle the idea of a real gas from a very intuitive point of view. And what this intuition will lead to is an insight from van der Waals.
Real gas or ideal?
Real gas, the intuitive real gas. How can we intuit how a real gas is different than a ideal gas? All right, and so I want to put our heads in the space of someone in the late 1800s, where microscopic physics doesn't exist effectively. We can measure energy, we understand electromagnetic theory. We have some sense that molecules interact and react with each other, right? But we don't really have an appreciation for the even statistical structure of microscopic chemistry and entropy and all of that. But van der Waals has a really nice idea. He says, what's the easiest thing I can do? Take the ideal gas law and fix it. What's the easiest fix I can do? It's the dumbest thing I can do. And what van der Waals assumes is this. So first he defines a potential. So he's got two particles of a gas, just like we had before when we talked about the Lennard-Jones gas. Two particles A separated at a distance R. And what he assumes is that the potential energy as a function of R, just like the van der Waals gas, when we talked about the Lennard-Jones, right? We said at long distance it goes as R to the 6th, and at close distances it repels R to the 12th. He does something even dumber. Dumber's not the right word. Simpler. Where he says that for any distance appropriately short enough, we'll call this the critical distance, which the critical distance is effectively the radius of the sphere. That here the potential is infinite. All right, so what that means is that the two spheres, they can't overlap. Right, it's a hard wall. These are what they call hard spheres. Right, so they can't overlap at all. I should say less than or greater than or equal. So these are hard balls. They're completely impenetrable. And then what he says is they're away, right? That there's some average attraction to them. Or R greater than R prime. It's just some number. Okay, so it's not distance dependent like it was in Leonard-Jones. That's just a number. Right? So his potential looks, if we were to draw it on the same plot as our Leonard-Jones potential from last class, the van der Waals potential looks something like this. This is the van der Waals potential. And then the Leonard-Jones potential on the same scale, let me fix this to make it a little deeper. It looks something like this, and there's a hard wall. This, whereas the Leonard-Jones potential smoothly varies. And increases like this. Right, so slight difference, right? There's some the Leonard-Jones has a distance potential, and the intensity, or sorry, the attraction rolls off at some distance, right? At infinite distance, there's no attraction. And then you can again, the idea is in the Leonard-Jones, the atoms and the molecules are slightly squishy. You can press into them. They want to expand back out, but you can compress them. So you have a smooth roll off towards infinity here. Or as van der Waals says, you either get all or nothing. This is what's called a hard sphere model. And Leonard-Jones is a soft sphere. Okay, and then so van der Waals asked the question now, what are the empirical consequences of this potential? He doesn't really do a lot of math. He's doing empirical science. He's measuring things in the lab, and he's doing some calculations. He is a theorist as well. He doesn't really understand microscopic collisions or any collision theory. That doesn't get these things. But he thinks intuitively about how these two effects, this attractive effect at long range and this extremely repulsive effect at close range, would affect the gas. And what van der Waals says is this. So VDW says ideal gas is modified in two ways. One is that now compared to the ideal gas, which has volume V, which measures the free space that the particles can exist in, there's now a region of that space the particles can't exist in, right? Because if I'm this particle right here, I can exist anywhere on this page except for within the range of A. Right, so if I'm this, right, so the effective volume that this molecule on the right sees is in some sense smaller than the whole box, because part of the box is taken up by the other molecule, right? They take up space. So the effective volume that you measure when you do your Pivner measurement or whatever, you measure your pressure volume in lab, it's been modified by the fact that the atoms fill space. And the reason why they fill space is because there's a region where there's infinite potential energy for other molecules to coexist. And so this is like an exclusion. Every atom has an excluded region where no other atom can exist in. And that's just saying that they fill space. So the repulsive potential has a space filling effect. And so from van der Waals' point of view, the volume of the van der Waals gas, if you will, in this picture, is the ideal volume minus the number of particles in the box times their effective volume, right? The exclusion, the volume of the excluded region, with the volume of these spheres. There's n of them. And van der Waals assigns this parameter, this size parameter, unfortunately, to the letter B.
Why is that unfortunate?
I guess it's not. I'm sorry, it's not. He also assigns something A, but A correlates to A. So I just mixed them up. It's not unfortunate. It's thankfully and B, right? And these are effectively what you could say is that these are the average volume of a particle. Right? Just like if you fill a box full so here's a really interesting thing you might not know. You have a barrel, actually a cube, with an empty cube. And you fill it with spheres of equal size. Does anyone know roughly what percent volume is actually filled and what is empty? Do you guys know what the packing efficiency of spheres in a cube are? Because if you imagine, if you set spheres on top of each other, there are going to be gaps in between the spheres where the spheres aren't lined up. And there's going to be these little areas on the outside between the spheres that you can never fill. Because those spheres they're not stackable, right? And okay, you probably don't know the answer to this question.
I'm curious now.
So it turns out it wasn't proved until like 10 years ago. It's about 67%.
Oh, I was gonna say that.
It's about 70%. And so think about it this way: if you have a box and your molecules are spheres, the most you can do is, in some sense, fill 70% of that box. Because eventually what you're going to have are a bunch of these hard spheres all stacked on top of each other. And there's going to be some free space and some accumulated free space left over, and then the spheres keeping up the rest of it. And that's about a 70-30 distribution, right? So even in real life, an ideal gas can't exist because spheres will eventually pack in efficiently. So they always leave 30% of the volume. Right, so very, very simple idea, right? We just adjust the volume by the amount of material that has been taken up. Amount of volume has been taken up by the spheres. All right, so that explains this region right here. Right, now how do we correct for the attraction? Well, the attraction does the opposite. Remember what we saw when we looked at those pressure curves for the different gases. We saw that in that, like, especially for methane, if it's a really high pressure, it's repulsive. But there's that intermediate pressure where the pressure that you read is lower than what you would expect from an ideal gas because of attractions, right? So attractions bring the gas in closer. There's a compression. So the pressure should drop. The observed pressure of the material should drop according to the amount of attraction. Right? But attractions are slightly trickier because they involve two bodies. Right? You can't have an attraction of one molecule to itself. That's not what we're assuming. There are such things, but in this case, we're just thinking about dumb balls that just have a very simple pairwise attraction to each other. And so it's a two-body interaction. You have to have two bodies for an attraction. You have a two-body average attraction. Okay, and the way to think about the units of this attraction, how it depends on volume, is to look at the first case. Every molecule, the volume gets modified linearly by the number of molecules in the system. This is the average volume of the atom. You have n of them. So volume is just proportional to molecules in this case. This is what we call a one-body interaction, a one-body correction, right? Because it's only dependent on the dimensions of one body. But here we have a two-body interaction. It's the interaction of two bodies, two space-filling objects whose contributions to the box go as V each.
So
So-
does that mean that it's gonna be, 1/2 of?
Not
two?
quite.
Or the average, sorry,
No.
not 1/2, the average, like both of them added together 1/2, like the average
No.
of the two?
No,
Okay.
it's not, unfortunately.
Okay.
But you got the right idea. It's not a sum.
Okay.
But let's think about this a little bit. So we've got these little balls here of some size, and we're interested in how pairs of them pull themselves together. Right? Each one of them brings into the equation 1 unit of volume. Right? This has units of B, which are liters. Right? And let's think now, right? This atom in particular has some choices for its attraction. One, I can look at the one nearest to it. Right there, so there's some other attraction to something that is nearby, but you can also imagine that there's another atom here that it could be attracted to, or another one here. Right, and so you have all these different attractions between pairs of atoms. Right, so we're summing over all, let's just say, all attractions. Okay. And so if we think about the total attraction, this is just a really, really rough math. And we sum out all the total attractions to atom A, where atom A is the center one. Right, so we have 1, we have 2, we have 3, we have 4. And let's say it has n atoms around it. So there's n attractions. Well, this is going to be the sum of the attraction from n equals 0. Sorry, I equals 0. We're going to sum from I to n, and we're going to sum over all the different pairs. So we're going to multiply this by I. And once you do that, you get minus I times I plus 1 over 2, which is proportional to minus AI squared. So the attractions go as the number of attractions squared. So what that means is that when you sum over all of them, the total attraction doesn't scale as the number of particles, but the square of the number of particles. And since the number of particles are proportional to V, that means the attractions are proportional to V squared. So you can think about each volume element, the units of V in some sense are the dimensions of one molecule. So therefore, the dimensions of two molecules in their interaction, a two-body interaction, has to be V times V. And you sum over them all. So it's V squared. Right? He shows that instead what happens is that the pressure changes. Right? We're thinking about how the pressure of the system changes with attractions. Pressure goes as 1 over volume. They're inversely related. And he finds that the change in pressure is proportional to this value A. And we got to add some Avogadro's numbers in here, n squared A over V squared.
Negative.
Yes, negative, because it's attractive, right? Because it brings things together. So we have two effects, and I know that's a little confusing, right? But the idea is that a one-body interaction, and we'll look at this in a slightly different way a little bit. Something that's due to one particle's property that's about size or shape has units of volume. And so anything that has to do with the volume of two objects interacting has to have units of volume squared. If there's a three-body interaction, which there are in real life, water, for instance, has a very strong three-body attraction to itself. That would be a V cubed therm, and so on and so forth. So what he says is that now we adjust the volume of the ideal gas by NB, and then we have this new term that gets added to the ideal gas law that subtracts off A over V squared. It's an adjustment. So what does van der Waals write? Well, we start with P equals nRT over V. Right? That's the ideal gas law. And then we add finite size, right? The size of the balls. nRT V minus NB. And then we add attractions, which is nRT V minus NB minus N squared A over V squared, which is equal to pressure. This is the van der Waals equation. Now, if you thought that I was a little hand-wavy with my argument here, well, van der Waals was too. Van der Waals says exactly what he said here, that the finite size should have a finite adjustment to the volume, and attractions should decrease the pressure since you're bringing things in, and it should go as 1 over V squared. Right. Obviously, this equation, once again, is just an approximation. Right? It's in some sense the next easy approximation you do after the ideal gas. It's still not, in some sense, physical, right? Because we haven't actually included any of the properties that are really interesting about intermolecular interactions, which is the fact that one, they're not hard spheres, and two, the interaction is distance dependent. What that would mean is that the pressure, that the net attraction would also have some pressure dependence as well, most likely. That's a much more complicated argument. But so this, in some sense, is not even up to the standards that we've set by our discussion about intermolecular interactions. But it gets us an additional step, right? In some sense, well, what we're doing is just we're blurring over the distance behavior of an interaction by saying either it's attractive or it's completely repulsive. Just a natural continuation. Let's see how much better this is. The important thing about this now, I should say now, is that now it's not a universal equation anymore. Because now there are these two numbers A and B. Right? And A and B are molecule dependent. Right? So now the relationship between pressure and volume is not universal, it's molecule dependent. A has units of liters per mole, and B has units of liters squared times bar over mole squared. All right, let's just look at a quick example. Let's just do a quick Gen Chem plug and chug. And let's look at how van der Waals compares to the ideal gas for methane. All right, so let's do CH4. All right, we'll do 1 mole. We'll do the volume to be 0.25 liters. And the temperature to be 273.15 Kelvin. All right, and I want to ask what the pressure is. So that's the only thing I don't know. Well, any of you guys can do this. I'm not going to work it out, but well, I'll just write some numbers. P is going to be 1 mole. I personally like units of bars for pressure, so I'm going to use 0.083.145 bar liter bar per mole Kelvin. Multiply that by 273.15 Kelvin. And then divide everything by 0.25 liters. Right? This is just Pivner. Right? And this is 90.8 bar. Okay, so we would predict that a methane at these conditions, small little beaker, 1 mole, freezing water temperature, we get 91 bar of pressure. What does van der Waals tell us? Well, the first thing we have to do, we have 2 new numbers that we have to define, right? A and B. Methane has values for A and B, and I've just pulled them off of Wikipedia. A is 2.3026 liters squared bar per mole squared. There's not really a lot to learn from that number. It's just a number. But this for B is a lot easier to understand. B is about 43 milliliters per mole. Right? This has a really easy interpretation. What this is saying is that on average, a mole of methane takes up 43 milliliters of space. That's pretty easy to understand. Right, and of course, if we think about it, our beaker here is 250 milliliters, right? So at 1 mole, it's already filling up almost, the molecules fill up 20% of the space. That's what that's saying. The total effective volume of the atoms is 20% roughly of the total volume, which is significant. So it's not surprisingly the pressure we're going to read is different because we've just excluded 20% of the volume. So we'll just go ahead and plug and chug. The reason why I like bars, is because an atmosphere is 1 bar. Nice and simple. So here's my first term, nRT, or RT over V minus NB. And then we subtract off our attractive term. We have to multiply by 2 factors of mole. Get the right units. And we put the units, the liters, down here in square. All right, so this is our van der Waals calculation. And the answer we get is 72.9 bar. Wow, huge difference, right? I just described that the fact that we now include the fact that methane takes up space and it takes up 20% of the space, and there's an attraction on top of it. The pressure you read against the walls is there accordingly about 20% smaller. Right? In fact, the correct pressure that van der Waals predicts is 73 versus 90, right? That's a huge difference. But the actual experimental answer for this well, neither are particularly good approximations. But as you can see, van der Waals gets it better, right? Van der Waals, in fact, overcompensates for the attraction of it. as we saw, remember that with weak molecules, right, you always have a repulsive force that's competing with an attractive force. But in the van der Waals expression, the repulsive force only kicks in right at that hard wall. But in real life, the exchange effect occurs at all distance scales. It scales as 1/12. It's always there. And so that will affect the pressure, increase the repulsion accordingly. And you can see the difference here between a very simple hard sphere measurement and a more repulsive exchange based reality of methane, which is much more repulsive. Right, but it gets you much closer to the correct answer. And this is super important. And I always tell this story every year when I give this calculation. That you're like, well, first of all, I mean, it should be obvious to you that there are situations in chemistry where this is a bad thing. That if you gave this, but you need this, that's a huge problem. 20% off. I mean, I don't like to talk about money and economics when it comes to industry, but I mean, that's 20%. You have some rare gas, that's a lot of money. Just as an example, a tank of neon. I use neon in my research a lot. Neon's a really, really great gas. It's not too sticky, but it's kind of sticky. It's fast, but not too fast. It's a really nice gas. It costs about $12,000 now for a single bottle. So if I have some flow experiment where I need to taper out my neon to be as slow as possible to facilitate my chemistry, I better make sure I have the right pressures and the right flow rate for my condition. Because otherwise I'm wasting 20% of my material. And I've had this problem happen to me before, an experiment. When I was in my postdoc, I was doing my first true kinetics experiment. And when you do kinetics, you need to know, especially in the gas phase, you need to know your pressures and your temperatures extremely accurate. Because we can't really measure volumes really, because you don't have like liquid, like a graduated cylinder. Well, we can measure flow rate, we can measure pressures, we can measure temperatures. And of course, that's good enough, right? That's all you need to measure gas properties. And so I was flowing in the gas into this flow cell. It was a molecule acrylonitrile, which is a double bonded, like an ethylene with a CN group. Very sticky, very polar. Amazing how polar it is. And I read off the flow rate and the temperature and basically calculated the pressure and the concentration of this precursor that I had from these numbers, and then reacted them and measured the rates of the product formation. In order to be able to figure out rate laws, I need to know how much material I put in. So if I double the concentration of my precursor and my rate goes by 4x, then I know it's second order. And so measuring kinetic properties. And no matter what I did, kept doing this experiment over and over again, the rates kept coming out 4 times larger than they should. It was predicting that basically my data was suggesting this reaction, which should have been first order, meaning double the concentration, double the rate. It was like 6x. It's like 3 times. It's driving me up the wall. 4x, 6x. It's always really inconsistent. I changed the temperature too, and it will also affect the results. So driving me up the wall. Couldn't figure it out. Everything was totally overcompensated. Something else was going on. Spent 3 weeks of burning my brain about it. And I went to go talk to my advisor about it, and we went through the calculations. And he said, "How did you calculate your concentrations?" And I said, "Well, I've got X amount of gas at this temperature, the flow rate. I know roughly the size of the reactor vessel. I'm just using Pivner." He said, "Can't use Pivner. Because the fact is that I was using a gas that is extremely polar, very, very strong interactions. In fact, we saw signs of interactions that are so strong, we were shocked at how strong they were. Molecules communicating across very, very long distances that they shouldn't be. But anyway, these molecules interact very strongly. And even though I was only at a pressure of about 10 microbar, 10 to the 5 less than this calculation, 10 to the 6 less than this calculation, a million times less pressure. It turned out that the moment when I switched to van der Waals equation, all my kinetics lined right back up. Because I had assumed that the gas was ideal, but that got my densities off by a factor of 2 or 3. So I was dealing with a gas that's strongly interacting with itself. And when you accumulate just these small corrections to account for the size and the average attraction of the gas, it all disappears. These things can even happen at low pressures and in the vacuum in really small instances. But when you're working at hundreds of bar, when you're doing industrial processes, you absolutely have to deal with the real parts of the gas. Because otherwise you'd be off by 20%, at least. Now, if we're only at 100 bar here, we're going to talk about situations in chemistry, industrial chemistry later on in equilibrium, where you might be at 400 bar, right? And there, the situation becomes even more extreme. And so we have to consider these kinds of things. This is why it's important. Okay. What can we learn from this? Okay, so we can just do this, right? This just teaches us that gases aren't ideal. And that we have an equation that can correct for them, or a big one, right? We can come up with an equation for anything. But what consequences does this teach? What new things about chemistry can we learn with these corrections? Besides just being more quantitatively accurate. Okay, that's only interesting to some people. But is there something new we can learn from this expansion of our theory? Because now what we've done is we've taken a gas and we've introduced two really big paradigm shifting assumptions. One, that the molecules have size, and the other one is that they're attracted to each other. So what are the natural conclusions of this? I want to show you a really cool plot. I want to look at a gas experiment, one more gas experiment. And I want to look at compression of carbon dioxide at isothermal conditions. Okay. So the way I'm going to do this is you can think of it a couple different ways. I'm going to show you how I'm going to do this experiment. I'm going to have a bath of water. And inside of this bath, I'm going to place a sealed container of fixed volume. And off the side of this container, I'm going to have an inlet that's connected to a tank of CO2. That allows me to fill this in with gas. And this thing is sealed. Okay, so I have fixed volume, and the temperature can vary based on the bath, but the bath is effectively a constant temperature bath. And what I'm going to do is I'm going to stick a pressure gauge in there. Do it in a different color. This is a pressure gauge. And I'm just going to feed that in to my computer. It's my computer. No computers look like this anymore. All right, so my input, so this is my input, which is just moles. And my output is pressure. So what I'm going to do is I'm going to plot as a function of plot pressure of my material on the y-axis. All right, and then on the x-axis, because I'm at constant volume, I can write it as moles, but instead what I'm going to plot is the molar volume, which is the volume divided by the amount of moles in the material that I have in there. All right, so it's just basically 1 over the number of moles at constant volume. Okay. So what this means is that as I go to the left, that means I'm putting more moles in. So this is increasing N, and this is decreasing moles. Okay. Now, what does the ideal gas law look like for this? Well, that's an easy question to answer. For an ideal gas law, right? We have the same formula regardless of temperature. For an ideal gas, we have P is equal to RT over V bar. Right? So this equation, regardless of what temperature I choose, an ideal gas always looks like 1 over V bar. All right, so for an ideal gas at some high temperature, I have something that looks like 1 over V. This is, let's just say, for instance, this is T at 50 Celsius. All right, and it looks like 1 over V. It looks ideal-like. Ideal-ish. Okay, what would happen if the gas was always ideal? What would this curve look like as I cool down? Well, the curve is just some number times T over V, right? T's just changing. So as T changes, the numerator is getting smaller, but the behavior is exactly the same, right? The slope is still R, and it's still 1 over V. So you just have the same curve, right? But it would just go lower. I'll just put another one just to show you that, right? So if I would go to 60, right? T at 60 would look like this. And that T at 48 or something like that would look like that, right? Right? And I could go to any temperature I want, right? It could be 0, it could be minus 300, it could be 1 degree after above absolute 0, I could go 10,000 Celsius, it doesn't matter. An ideal gas compresses exactly the same anywhere in the range. Now, what happens in real life? Well, what I notice is that as I start to cool towards, let me give you the correct number. As we start to cool towards 30 degrees Celsius, let me give you some labelings on this. I haven't completed this yet. So let's set the pressure. Let's get some scales here. So this will vary from 40 to 100 in atmospheres or bar. Put 60 here, 80 bar. And then this will range from 0.0 to 0.4. Okay, so we have fairly high pressure. So it's a fairly small container. If we put a mole in, right, this container is on the order of, we put a mole in, this is on the order of about 200 milliliters, right? If this were a mole right here in the center, 200 milliliter container. All right, so it's a fairly small reactor, or a fairly small amount. And these are the kind of pressures that we would see at these temperatures for that gas. But what we see as we start to cool is that this curve starts to deviate. So when we get to about 32 degrees, right, it starts to decrease like we want. But instead, what happens is there's a small curvature change in the equation. Something that looks like this instead. All right. What we notice is that there's, in some sense, a small hump that appears. As we start to cool very, very slowly, in fact, we just bring it down another half a degree or so. we find that this hump flattens out at one point and changes curvature. And as we continue to cool, let's go to like 30. Do one more. That this hump basically becomes a flat minimum. And then as we finally cool to the lowest temperature possible as we can, we find that that hump goes longer and longer and longer as we go. All right, so the thing I want you to focus on, let me do it in a different color, is the fact that as we approach a certain temperature here, and for CO2, it's about 30 degrees at these pressures, at these conditions. We notice that we transition from a curve that looks like 1 over x or 1 over v to something that looks a bit like a cubic function. It's got like a flat area, and it also has a change of curvature, right? We're concave up in this direction, and then there's this region that's concave down or flat, and then we get concave up again, right? There's a curvature change as well.
And that's for an ideal gas or a
Non-ideal gas. These are experimental. These are experimental.
Okay.
This is what we would expect for an ideal, and that's what we see at high temperature.
Okay.
But I'm saying as we start to cool, that we start to deviate, that curve starts to deviate away from ideal and leads to this kind of weird cubic-like looking function. All right, eventually as we start to cool even more, I'll just draw one more for example. That region that where it's flat gets even wider. Strange. So something's appearing that doesn't appear before, right? Now, what's changing, of course, is the temperature, right? So as we change the temperature down, we're pulling the amount of heat that's in the system, right? So whatever forces that were present there are no longer getting soaked by the heat in some sense, right? So this is the attraction starting to build, if you will. But it changes the shape of the function considerably. But here's the more important thing that we notice, that's noticed here, is that there's some temperature where the behavior goes from having no hump and being concave up the whole way to a hump forming, and that hump widening to a region in which the derivative of this function is flat. Now, what does that mean? Well, it means that in this region of, so what I'm doing is I have my material at some temperature, and I'm feeding it CO2. So as I feed in CO2, I'm moving along this curve, and of course, as I feed in CO2, the pressure increases, right? When we do it at high temperature, right? Pressure increases, and as I feed in more CO2, the pressure continues to increase. Here that happens at low pressure, starts to increase, and then what we see as we start to add more CO2, the pressure doesn't increase anymore. Not only does it not increase anymore, it's just flat. And then eventually, we put in enough CO2 that it starts to jump up again. Pressure starts to increase again. But as you can see, the pressure starts to increase much faster than it did before. So something new is happening. So some new behavior here. So let me just kind of summarize this. At sufficiently low temperatures, and sufficiently high density, gas can be added with no pressure change. Now, how the hell does that happen? How can I take a gas and feed it into a container where there's other gas? And I know I'm flowing it in there, I can see it flow in, but it's not increasing the pressure at all. What could be happening? Think about that for a little bit. What could possibly, first of all, where do the molecules go? right? If
They're
they're
not
not,
changing phases.
yeah. Can you expand on that a little bit more? Why would the pressure not change?
Because, okay, so because the reason why the pressure doesn't change is because once it turns into a liquid, it's going to take up only the amount of space, it sticks together more, and it only takes up the amount of space as its volume. It has a set volume, and yeah,
That's not pushing against the walls.
that's not pushing against the walls,
Correct.
but will fill up as much as it can of the walls.
That's right. And then eventually what happens is. Then what would you explain about
And then
this?
and then it would stop. What do you mean?
So
Oh,
this
then it
is,
keeps good, the
so
pressure goes.
what you're claiming, this is right here is condensation.
Uh-huh,
So you have gas, 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 and then the system condenses and you
Right.
start to form liquid as you add gas.
right,
What happens
and
here?
then it turns into solid. Or,
Not necessarily solid. We're not at the temperature which
it
CO2 freezes yet.
Sorry, that's what I meant.
Not freeze-
We're not.
It could maybe freeze,
Okay,
but here's the other thing that you can consider. So we'll finish up what Angie says. Angie's exactly correct. What's happening here is the only way that you can feed in gas and it not affect the pressure of the gas on the inside of the container is for that gas, for those new molecules to go somewhere else. They can't escape. So the only other logical conclusion is that they condense out. And so what's happening here is you're feeding in gas, 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 and eventually you hit the condensation point where your pressure is enough that it starts to condense. And here then what happens is that every molecule you put in after that condenses out. And the system slowly converts from gas into liquid.
and then you get to a certain point where the more you add, it just turns.
It's just liquid at that point. And so in order for the pressure to increase rapidly here, what's happening here is you're just feeding, you're feeding more molecules into a container that's already more liquid. So you're compressing, at this point right here, the container is already full CO2 liquid. And so to put any more liquid in, the pressure will increase because what you have to do is compress that liquid to fit more in. Right? Imagine taking an already full container and putting more water in it. How do you do that? The only way to be able to take a glass and put more water in it than it already does is to increase the density of the water. And the only way to increase the density of the water is,
the temperature.
well, we can't do that because it's constant temperature.
Oh, right.
So the only other way to compress the amount of volume that liquid water fills is to compress it. So if you want to put, at this point, you have 250 milliliters of water, of CO2 liquid in your container. And in order to fill 251 milliliters of equivalent amount of CO2 liquid in your container, is to compress the original 250 milliliters to 249 milliliters and put in that additional milliliter, right? You've got to compress everything to open up some more space. And that's very hard to do, right? It's very hard to compress a liquid. So the pressure, right, in order to fill in more molecules, you have to compress the gas, which means the pressure has to skyrocket in order for that compression to happen. So to break this down, this is a little messy. But here in the first step, we just have gas injection. And then what we have at some point is condensation. Right? And then what we have during this flat period is just, well, it's just condensation too, but it's just liquefaction, right? You're liquefying the system. And then finally, you liquefy the whole system, and then you only have compression left. Right? Angie is correct. If you compress this enough, eventually it will solidify, but we're not going to worry about that. That's a different one. Solidification is a much more complicated process than this. Liquefaction. All right, notice that where this came out of, well, we haven't proven it yet, but what we're going to find in the next 10 minutes is that the van der Waals equation predicts all of this. The van der Waals equation is all we need to get liquids out, right? So by turning on the fact that molecules have a size and they have a finite attraction, we're going to see is that in fact, the exact behavior we see for a system that's both liquid and gas in coexistence can be described exactly by the van der Waals equation. These two small minuscule forces are all you need to get phase transitions. Solids are a slightly different thing. So let's explore that just a little bit mathematically. Right, can I get this behavior from the van der Waals equation? I'm going to plot this. I'm going to put this a pre-made version of this plot that I made up on the board really quickly, just so we have it. And I want to focus in on a particular point on the curve. Probably on lecture 3. Yes, here it is. Beautiful. All right, so this is the exact same plot I gave you. I'm just giving it to you in a slightly prettier form. And what I want to point out is that as I cool this gas, right, these are the same things that I drew before. If I cool this gas, we go from a region that's ideal, meaning it's concave up and there's no curvature change, to a set of curves where there is a distinct curvature change and also a zero derivative, a minimum, or an inflection point curve. Right here, there is no inflection point. This entire curve is concave up. But eventually you're going to hit a point where there's like a critical condition where the curve has exactly one flat point, right? An inflection point. Which the thing has labeled critical CP, right? This is what a mathematician would call it, an inflection point. Right? And an inflection point is a point where the derivative is zero, but also the curvature is zero as well. What that typically signals is that your curve is moved from concave up to concave down, or vice versa. Right? We can see that here. Right here, the certain thing is concave up here. Right? And here the curvature is concave down. Okay, so it's flat here, right? So the derivative is zero, but you also have a curvature change, which is the second derivative is changing signs at that point from positive to negative. So the second derivative is zero here too. So there exists a point VT such that dP/dV at constant temperature is zero, right? That's the slope of this curve. This is the slope. And that the second derivative of the pressure with respect to the volume. Sorry, let me fix my notation. Constant temperature is zero. Right. We call this point on one of these equations, these curves, this is called a critical point. Now, what does the critical point measure? Well, the critical point measures where what we call the isotherm, right, where the compression curve goes from a situation that's pure gas to one that has condensation. So the critical point is the point in physical space, physical parameter space, point in physical space. So what by that I mean either volume and temperature or pressure and temperature, depending on which way you look at it, such that at any T lower, condensation occurs and above only a gas exists. Okay, so what this means, in fact, is that for any liquid, there is a condition, some temperature, some density, or molar volume, however you want to think about it, where there is no liquid. No liquid can ever form. There's always going, but there's always going to be a point in which, in some sense, the liquids turn off. And then you get liquids at a certain set of conditions. Eventually, you get to a certain point where the liquids freeze out and you get solids. That's a different thing that we'll talk about later on. But liquids are not a universal concept. What this means is that there are seriously temperatures and pressures, right? As you can see it here in CO2, right? At this temperature and these pressures, there is no liquid CO2. It does not exist. You can never generate. But the moment you cool it down to this critical point, there are now points in which condensation occurs. Right? So this is some magical point where the liquid turns on and off. Let's show that this exists for the van der Waals equation. Okay. So we want to show that there exists a point. Whoa. What does that mean? Maybe. We want to find out where condensation turns on for the van der Waals gas. So what we want to do is we want to solve these two equations for the van der Waals gas. Is there some pressure, volume, and temperature, or volume and temperature, let's just say, where this equation, these two equations are valid? What values of V and T or critical point? Okay. Okay, so we have to take derivatives of this expression with respect to V and then set them equal to 0. Right. I'm going to simplify a few things. We're going to write this in terms of V bar. That allows me to get rid of all the A's or the N's. All right, now I can take derivatives of this expression.
Wait, you wrote V bar next to P at the very beginning. That didn't mean to be V bar.
That didn't mean to be. Yes. Thank you. Thank you. I'm not always consistent. So let's just quickly run derivatives of this. This is going to be 2A over V bar cubed minus nRT, sorry, get rid of the N, sorry, over V minus NB squared. That's the first derivative. And this is going to be equal to 0. And then we have to calculate the second derivative of this expression. So the derivative of the derivative, this is going to be 2RT V minus NB cubed minus 6A.
Wait, I thought we got rid of the N.
Sorry, thank you. Yeah, you're right, we did. Over V bar to the 4th. Set these equal to 0. Okay, so we just have a little bit of algebra to do here. I'm not gonna do it. In fact, there used to be a problem set, part of a problem set to make you guys do it. But I'm not gonna do it. But anyway, it's probably not that hard to believe that there's a V and a T that solves both of these.
Wait, that's a 6A there, right?
Six.
Okay. Sorry.
No, that's okay. It looks like a B, I'm sorry.
Yeah.
Let's. That looks even worse, doesn't it? So what does a 6 look like compared? So this is a B.
I would put a 6 like make it more that this part goes more downwards. Like this.
Can you draw it on here for me? Oh, okay. Beautiful, thank you. When I was in kindergarten, I used to get frowny faces for my writing. You can tell why. Still the case. It's not too hard to convince yourself that this is probably, we just have to eliminate some B's in here. And then you get a nice quadratic equation. It's not too bad. There's just a little bit of algebra.
So then they equal each other.
Yes, you set them equal to each other, eliminate the denominators, and then you get a cubic equation or a quadratic equation that you solve. And let me go ahead and write down the numbers for this. We find that there's two points, TC, which is the critical temperature, and the critical volume. Right, so these are the temperatures and the volumes that give you that curve where you have that inflection point. That's where the liquid condensation turns on. VC is really easy. It's just 3B. And TC is 8A over 27BR. It's amazing how simple these are. And you can put these together with with the van der Waals equation to get the critical pressure, which is A over 27B squared. So these are called the critical coefficients. Right? They specify for a material the critical point where condensation becomes possible. At temperatures or pressures, temperatures greater than TC or molar volume less than this, pressures less than this, there is no liquid. You never form it. Well, what van der Waals shows us is that when you just turn on attractions, very, very weak attraction. Remember, they're not very big. We saw how small they are, right? They're on the order of, a hydrogen bond is 5 kcals per mole. A normal carbon-carbon covalent bond is about 150 kcals per mole. And so a strong intermolecular interaction is still a tiny fraction of a bond. We have all these little effects, but the important thing is that not only they're all little, but we have millions and millions and millions of them in a box. They accumulate very, very readily. And just like the sizes, the atoms are very, very small, but in a macroscopic box, we have millions and billions and trillions of really, really small volumes. And so they start to add up. And so what we have are just very, very diminishingly small forces that in the aggregate become significant. And they're just significant enough that at certain conditions, liquefaction turns on. That you can liquefy. Intermolecular interactions are solely the source of the other phases. Otherwise, everything would just be an ideal gas. But just having these small little dispersive interactions between things allow you to liquefy things. Of course, the stronger the attractions between the gas, the more excuse me, right? The stronger the liquefaction is, right? And we can kind of see that here. Right? If we look at the critical temperature, right, it's a function of A and B. So the attraction, in some sense, the temperature is modulated by the attraction positively, but also by the size. But they're roughly equal to each other, right? So as we'll see as we explore this just a little bit more next class, moving on to liquids and talking about liquids, that this balance is super important. Not surprisingly, the critical volume only has to do with the size of the molecules. Right? You have to make sure that they're all in roughly the right space. You don't want them to be too close together. You also don't want them to be too far apart. Right? And we need to balance between the size and the attractions. You have to find that neat spot. If you have a too congested of a material, you can't make a liquid because you generally you make a solid, right? It just there's not enough entropy in the system. You don't have enough heat. And so, but you don't want it to also be too hot and too weakly interacting because then it'll never form a liquid. And so liquids are kind of a really, really kind of like Goldilocks region of physical space because we found the perfect balance of the repulsions that keep things as a gas and the liquids that want to solidify things. And so it's about finding the right balance between the attractions and the repulsions is where liquids exist. Right? So that sweet spot. And it only exists because of these interactions. So what we have now, by just kind of walking through gases and turning on interactions, we now have a new process that's formed in our system that we have no idea how to measure. This is only looking at the gas. Right? But what we have is the gas disappearing into a new phase. We have no concept of how energy is flowing in this system. All we know is the molecules are now disappearing and our pressure meter is no longer measuring them. So what we're going to now have to look at is expand our vision of our little reactor. We need to stop thinking just about the gases, but we also need to think about what's happening in the liquid phase as well, and at the interface. And what happens when you take a gas that's a gas and then suddenly it becomes a liquid? How does the energy change in that system? So we're going to have to start thinking about how to measure the energy changes of phase transitions. How do the properties of the materials vary between a gas and a liquid? Right? So we're going to have to start thinking about those things next. That will now introduce us into a new type of box. We'll move away from isothermal boxes and start thinking about isobaric and isochoric boxes, things where constant volume and constant pressure are also a thing. That will be much more helpful for liquids because in liquids, we don't care about the pressure anymore. Right? So maybe we'll start thinking about things at constant pressure and we'll find that that really helps us start to pin down what's going on in the liquid. Okay, guys, have a good one. I'll see you Thursday. Hey, what's up?
I had a quick question about the problem set.
Uh-huh.
So for problem 1.5,
Mhm.
you told me and Caitlin that we should set it up kind of like this.
Mhm.
When we calculate our abundance, it's all negative.
Yeah, you gotta take the exponent to the.
Okay, that's what I
Yeah,
thought.
yeah, you gotta go back to the previous, the way that they're represented in the data. Yeah. And I would recommend taking your predictions and taking the exponent to them instead of taking the log of the experimental numbers. Because percent error in logs is different than percent error in numbers. So when you do everything in logs, it gets a little funky. So just take an exponent to anything that needs it that's negative, and that should work.
Thank you.
Yep. What's up?